So today we'll have a look at a test bed that we are doing in near Davis. Since you guys are all familiar with our test bed over here, I'll draw some comparisons go along. I'll also spend some time talking about the research that we are doing that will eventually leverage the test bed that we are building. So I'll have a very brief introduction because most of you know about what I have in the introductory slides in here. Then I'll jump into the description of the test bed that we are building and in the process of expanding it. Then we'll move on to the research efforts that we are going to leverage from this test bed. While I'll be talking about the research, instead of just picking up one particular topic and going into the details like a paper presentation, I'll give you a rather not very high level, but a higher level view of a variety of different research efforts that are ongoing in our lab. That will give you a glimpse of kind of research activities we are involved in, and we can talk offline on any of these issues that if you would be interested in knowing further. In the concluding remarks, I'll give you my personal view of what I feel the area is heading towards. So mesh networks, as all of you know over here, but let me go ahead and define it because people define it in a different way. These are composed of wireless access router that facilitate interconnectivity through multi-hop paths, and the mesh may be connected to internet through one or more gateway routers, and the access points are usually, or access points which are known as the wireless routers, are the nodes, which may be homogeneous or heterogeneous, may be connected in a flat or hierarchical manner. So this is the picture. Usually in any enterprise environment, the access points are connected by wired lines. If you remove those, then you can create a mesh, and you can see a couple of gateway nodes connecting to the internet. So some of the applications, this is a picture of the RoofNet project at MIT. You can build community networks. You can have enterprise networks, enterprise-wide networks. In fact, we are involved in a project in collaboration with HP on having home mesh networks, mainly in the context of a digital home project at HP, where you have for entertainment purpose, you have small mesh networks in home. You can have local area networks in hotels, mall, parks, trains, subways, or metropolitan area networks like Philadelphia Wireless, Chicago Wireless, or San Francisco Wireless, those kind of network. And you can also have ad hoc deployment of mesh for public safety, rescue, and recovery effort, where you put nodes on the service vehicles and then connect them on the fly. Okay. So again, since all of you are very familiar in the introductory stuff, I just flash through the slides. Okay, so getting back into the test bed that we are building, this is a very beautiful picture of Lake Berryessa over here, which is near the Napa Valley area. To give you geographical location, this is halfway in between Davis and San Francisco, so about 40 miles each way. In the middle, so this to the right of the lake is a ridge, which is it's a big ridge, and I'll show you a topological picture also, which is about 2,000 acres of wilderness. It's a natural reserve, and the key thing, many people have asked him, why did you pick over there? If I want to look for a large place in California, it's very difficult to get even 100 square feet. Getting 2,000 acres is extremely difficult. The nice thing is this entire ridge is owned by UC Davis. It has no public access, so nobody else can go in there. So that was the main reason, to be honest, why we picked this place. It has very hilly terrain and heavy forest growth. So eventually, if we want to do some study on physical obstructions and those kind of things, we have all the variability in here. The nice thing about this ridge is that the main purpose of for which the ridge is being analyzed now is it's apparently a gold mine for ecological researchers, because of the presence of some unique flora and fauna and some small endangered species of animals in there. So I've been told that there are about 50 research groups, ecological research groups across the whole world, people from outside the US also, they have been using this ridge for their studies. So for example, before we went over there, they had to go there and collect the data and then come back and analyze it. The ridge is not very friendly. There are no roads for accesses to anything and all that. So when we go there, we use the ATVs, the all-terrain vehicles in order to move around in there, and there are peaks and valleys, deep valleys, and so on. So things will be more clear as we move along. So when we talk to the press, this is the first point we mentioned, that we are helping out the ecological studies. Okay, that's not the real goal that we have. So, but we put that as the first point, and in fact we do it. I mean, I shouldn't have said that what I said, because we do in fact support the ecological researchers. Okay. The motivation from a networking point of view is to create a test bed for running experiment in a completely interference free environment. So prior to this, this was not the first idea we had. We'd build a test bed on campus. Now and my current research is focused more towards very micro level analysis of behavior of protocols at lower layer, impacts of protocols, networking layer protocols on MAC layer, or MAC layer protocols and underneath, and so on. So to do those kind of tests, a lot of time we were worried about, and as with any experimental results, every run we do, we found different results. Usually it varies, but the variation was quite big, and most of the time we couldn't figure out whether it is because of the neighborhood wireless access point or not, and so on. And it's difficult to find interference free environment. I had a few undergraduate students scan the entire city of Davis, which is a very small city, about 5 miles in diameter or 6 miles in diameter. So we had 5,400 access points they could detect. Many people don't broadcast their SSID, but at least there were that many. So you can just imagine the density of access points in urban areas. So it's very difficult to do some experiments in those kind of environment. Again, don't get me wrong, I get this question in almost every talk. So before I get the question, let me clarify that the goal here is not to do performance evaluation, because in that case you need a realistic environment with all interference and everything. The goal here to do fine grained analysis of protocols or schemes that you are trying to study, that will help you design better schemes or better techniques, and that will eventually allow you to analyze it. Once you have that, you can run it over your San Francisco MES or Chicago MES, whatever, for realistic evaluation of the performance. If you have any questions anywhere, feel free to interrupt me. That's what I've said. It helps in designing an analysis of new protocol, and it provides very detailed anatomical analysis. If you want to do sensitivity study, what impacts what by how much, this is a good test bed to do it. It's not for performance evaluation, but for design analysis, and thus it complements the urban area test beds. I'm not saying that this is an alternative, but it will complement whatever is proposed, let's say in Ginny and all that. So it will help. So getting back to, let me give you a picture of some of the scope that we are dealing with. So in that area, very seasonal weather, there are a lot of wildlife that we have to deal with, and these do impact the design process. I'll tell you why. There are all these animals: deer, frogs, snakes, salamanders, mountain lions, bears, and of course quails. So the unique feature that I claim we have is it is deployed in the face of various topological and technological challenges. It's currently operational, and what I mean by operational is it's not only the network is working, but it also helping the researchers in ecology. To some extent it's helping the networking researchers, but the scale hasn't been too big, but it's certainly helping a lot to the ecological researchers in their work. And there are actually, I was told by them that there are 2 graduate courses where the students are doing work where they use our network, and we see extra traffic because of that. The area, again, I've mentioned this, the area is free from any interference and any other electronic noise. There is no cell phone coverage in that area also. It has wide variation. We have actually have wide variation and configuration options, and more are envisioned, and I'll talk more about that. The other interesting thing is the bottom line over there, which may not be too interesting for us, computer science or EC people. It runs completely on solar power, because there is no other option actually, because there is no utilities over there. So anything and everything that you will see is actually being driven by, the entire network runs over solar power. So the network architecture is, we are using heterogeneous nodes and heterogeneous network architecture. I'll elaborate more on that. Each node right now utilizes dual radios. So we have 2 radios per node, and we are using multiple orthogonal .11g channels. Okay. So each node right now has at least one directional antenna, one omnidirectional antenna. Some of the nodes have more. Again, the reason is, don't get me wrong, the goal here is not to provide just a network with very high performance. That's not the reason for multiple antennas, but if you want configuration of different type, we should be able to provision those. Right now we are supporting multiple channels, multiple radios, multi-rate transmissions, multiple antennas, and of course in multi-hop pattern. So the way the network architecture is designed is there are 3 layers. Again, this is layers in a very loose sense. We have the researchers, they collect their data using sensor networks. I'll show you some examples. So sensor networks you can consider as the bottommost layer. Then we have picked up some of the mountain peaks. This area is, as I said, is very high peaks, deep valleys, and so on. So we have picked up a few mountain peaks where we have powerful directional antennas. And purposefully we create long links and short links. Let's say you will say that, okay, dot 11 is not designed for long links, but so what? We want to say what happens when you use long links. So you will see link as much as, I think the longest link that we have is around 1.3 miles. Okay, and we have really short links also. So on the peaks we have created high bandwidth connections using directional antenna, and from the sensor network to the backbone, if I may call that, we use multi-hop communication. Okay, so again, as I said, this is not strictly hierarchical or anything, but loosely there are these 3 layers. Let me show you the topological map over here. So to give you some idea about the dimension over here, we are looking at 3 miles in the horizontal directions and 4 miles from top to bottom over here. This is the topological view. You probably cannot read it from there, but the heights of the different peaks of the mountains are written over there. It varies somewhere around 14 feet down to really deep places. So the nearest access road is over here, and the bottom red point that you see over here, this is where we have utilities, and to get connectivity to the internet we have a T1 line from here onto the campus, which is about 35 miles away, and from there it goes to the internet. So this is where the utility stops. Everything above here is powered by solar. You see all the red dots. This picture is a little bit dated now. Currently we have 12 nodes operational. This probably doesn't show all of them, but so one extra actually. This is one interesting node that is being deployed as we speak. This is a node actually floating on the water. So we have a floating buoy. There are some researchers, they are studying some water quality in the lake over here. Just to help them, we have a floating buoy. We are working on the power supply over there, and again we have to deal with issues. There is a ridge over here, so it cannot connect to the network, so we are bouncing it up from the other side of the hill to our network. Most of the regarding deployment issue in the second round that we are starting now, we are trying to deploy as strategically, but in the first round it was on a need basis. So because they wanted one, we are putting in here. While we are building this, there was a forest fire. In California, forest fires are quite, it's not a rare event. So there was a forest fire over here. So some of the ecological researchers wanted to study the impact of forest fire on some organisms over there. So we put a node over there in order to collect their sensing data and all that. So again, not all the things like from here to here you cannot hop through this because of obstruction. So this is a kind of a topological view over here. Again, an incomplete one. We have more nodes running in there. So intentionally we create, like this link is about 1.3 miles, this is about 1.1 miles, not drawn to scale over here. There are some real short links and so on. So we have tried to create as much variability. Yes.
The sensor network that you mentioned is consists of nodes apart from these nodes, or is this the only set of nodes?
No. Sensor networks is completely independent. As I said, in fact, we are not even paying for the sensor network. We have the researchers pay for that. We help them deploy it and whatever. But sensor networks is completely independent. So all we need is make one hop to our mesh. Okay. So I'm focusing more on the mesh networks. Okay. Sensor network is not a part of this. Any other questions? Okay, so getting into some of the nuts and bolts, we have so the other thing that I forgot to mention over here is note that we don't have, unlike Orbit, we don't have the luxury of creating a control channel in the wired or anything environment, because it's given the conditions over here, it is impossible to drag wire from one node to another node. if this is, as I said, if this is 1.3 miles as the crow flies, the wires could be 5 miles or more, actually could be 10 miles or more. And I mean, I've talked to some of you over here already. Since orbit 2 is going to be outdoor, in outdoor the logistical issues are a lot more complex than the networking or the scientific issues, okay, and I'll point out some of those as we go along. So it's almost impossible for us to even get permission to put a wire, any kind of wire in there, because keep in mind there are endangered species in there which are highly regulated by the government. So we are completely using off-the-shelf equipment. You know, I bet all of you must have seen or heard about these equipment. So we buy the Circuits embedded system board and basically add extra memory to it and use the Atheros chipset wireless card. And I'll show you some of the antennas that we use. We initially had 200 millivolts power card, but wasn't enough to drive some of our longer links. So we changed that to 400 millivolts. We use the MAD Wi-Fi wireless device driver. So again, you know, pretty much standard stuff that you know, most of the other test beds have used. There are two types of antennas that we are using. The omnidirectional antenna is the 7.4 dBi, and these are rather cheap antennas, and the directional ones are pretty good antennas because these are needed for the longer links. So the status is as follows. We have 12 operational nodes right now, and we have planned expansion to 30 nodes hopefully by the end of this year. For us, you know, the scale is when you go outdoor, the scale is actually one at a time. You cannot replicate like from 4 to 8 or something, and I'll show you also why. I'll show you some actual measurements. The bandwidth varies from 2 to 25 Mbps, which is pretty good. You know, when we go to 4 hops, the bandwidth drops to about 2 Mbps. And if you look at, if you read the leading MES commercial vendors like Tropos or even Cisco's white papers, they say, you know, at best you should go for 2 hops. Beyond that, performance starts dropping and all that. With multiple channels and powerful antennas, you can go to higher number of hops. Again, we are, based on my experience, I would say beyond 4 or 5 hops, it's difficult to get any meaningful performance. But our target is to go for 7 to 8 hops, just to show why things don't work that long, okay? Because the goal here is different. So I've already said we have used all this multiple stuff in there. One advantage we have is we don't have to generate fake workload. We sometimes do in order to get specific measurements that we want. But since it is already being used by ecological researchers, most of their sensors are actually streaming videos and audio sensors. Okay, so we get fair amount of workload traffic already in there in order to do some quick measurements from there. And we are, as we speak, we are collecting data 24/7. So we are collecting a lot of data. We have all the telemetry system at all the nodes. So the telemetry data that we collect include are overlapped over time: temperature, wind speed, humidity, light intensity, and all the works over there. And on top of it, we overlap the networks data, the signal strength, the packet loss ratio, round trip time, throughput, and all those information. So we are collecting a lot of those. We'll eventually try, and we are actually looking at to see if there is any correlation. Yes.
How do you collect the data? Like these are all dispersed. You collect the data and use the same network to store it.
Yes. So okay, should have mentioned that. So what we are doing is, as I said, this is where we have power supply. So we have a huge storage over here, a server and a huge storage. So basically we collect the data through our network because we don't have any luxury of having any wired network or anything. So we collect the data over the wireless network also and dump everything over here. And we have, as I said, we have a T1 line from here to campus.
So on a continuous basis, or you collect the data at each nodes and then at night you dump it or something like that?
Periodically, because for some of the ecological studies, night time is the busy time. So we
don't have any storage in each of these nodes? Or
no. We basically ping them and collect it and then do it. When I say continually, I should say periodically. It's not like, you know, every second we are getting the data or something. Any other questions?
400 milliwatt is used on these long links with the directional antenna?
Now all of them actually we have changed to once we were changing, we changed all of them to 400 milliwatts because we don't know how we are growing in future, so we changed all of them. But with 200 milliwatts we had the problems of not reaching those longer links.
But if you change all of them, doesn't that result in some inefficiency in terms of interference where it's not needed? I mean, for the long links, you need that power.
Yes, yes, yes. And again, you know, efficiency or inefficiency is not our worry because we want to see if it is inefficient, why it is inefficient. So that's the purpose. Again, as I mentioned, you know, all the nodes, almost all the nodes have at least video sensors. Some of them have audio sensors, and all the nodes have telemetry devices. Let me show you some pictures and clarify a few more things. So this is actually an interesting pond. That's why I put the picture first. Somebody from University of Michigan, and this was this got press coverage in the local newspapers also. Somebody from University of Michigan is studying some specific kind of frogs in that pond. So he has these acoustic sensors which you cannot see around the pond, and what we do is it makes one hop acoustic sensors to an omnidirectional antenna which is over here. Then, you know, for the next hop it uses this directional antenna. The other components over here is as I said, everything is driven by solar power. So we have solar panels over here, solar battery is just behind it, and the box that you see over there that houses our board. Again, you know, it might look like a simple box, but we spend a lot of time and effort in, you know, designing that box, because first we had to set a box which worked fine. Came summer, when the temperature gets very high in this area, all our boards fried. Okay, so we had to change the box and, you know, put thermocol lining inside there to cool it off and all. Again, we have to worry about other things. This is a quite expensive box because in addition to everything, we have to make it weatherproof as well as bear proof, because bear wants to fiddle around with anything new in the environment. So we have to, you know, take care of those issues also. Let me show you a few other pictures. This is one of the nodes that is in the backbone. Again, when I'm talking about backbone, we are still in the wireless medium. So this is one of the top peaks over there. So we have the power supply. So here we have bigger solar panel with the battery in there, and this is about 50 foot high. There are three antennas in here, an omnidirectional one here, and there are two directional in here. The reason, again, you know, you must have seen this in your lab also. If your antennas are close to each other, they interfere a lot. It's not marginal, they interfere a lot, even if you use completely non-overlap channels. The near-end interference, you know, sometimes if you are within less than 1 feet or something, your throughput could drop down to a single digit number, in fact, even if you are using completely non-overlapping channels. So because of these are high gain antennas, you know, the distance of separation is a little bit high. So these are some of the experiences. You know, I would admit that we didn't start with having all the antennas separated like this. We put everything on the top, nothing worked. So, you know, out of experience, you know, we changed to this. The other things that you see over here is in the top, if you can see that triangular, black triangular thing, that's the telemetry device which collects all the telemetry information. Okay. And the goal there is we want to see eventually what is the correlation between the telemetry data and the networks data. So again, it has not been long, but just from the initial studies, you know, we could see there is a strong correlation between humidity and signal strength. We could see a strong correlation between wind speed and RTTs. You would say why, you know, physics doesn't say that. The reason is wind speed does create swaying of the trees and everything and the poles, and so that creates signal strength variations. The round thing just underneath that triangular thing that you see, that's actually a very powerful video camera, and we are continually streaming video from there. So again, most of the nodes that are, so if you go to the QuRiNet website, you have right now we have access open for anybody who wants to access the audio or video sensors. So you can, so we have, you know, you have buttons to click that video from one hop through 2 hop through 3 hops, and you can compare the quality of video and all that. And there is this is probably at 1 hop. So all the nodes have similar very powerful cameras. Actually, if let me claim this and you can verify it, if there is a small bug walking on a thin blade of grass half a mile away, you should be able to observe every movement of it through this video, because that's what the precision needed for some of the ecological studies. Okay, and obviously when you go to 3 hops, you can see that the quality going down a little bit for obvious reasons. For the acoustic sensors, you have to load up some patch in your thing in order to hear the voices, if there are any frogs in there or not. Similar, the other things regarding access, I can go there, or actually let me be honest, my students can go from anywhere in the world and can take RTT measurements or throughput measurements between any 2 nodes, any number of hops and all that. We haven't yet have spent time in creating a GUI or user access from anywhere else in there, and we have to again figure out how people deploy. So these are a lot of lessons that we have to learn from the Orbit lab, because we this project was initially funded by industrial sources where the goal was not for open access, but recently we got money from NSF, so now we have to spend some time in making it open access eventually. Okay, so here are some of the other nodes at different locations in there. So you can see most of the nodes have at least 2 antennas. This is another pond. There is some different kind of studies going on in here. Picture of another node. This is where we are collecting some data probably. And again, so let me, before I get to the solar part, let me point out a few things over here. As I said, every node, it takes us less time for us to deploy the node than to get approval to deploy a node. So for example, putting something like this in a reserve where there are endangered species and so many research going on, it's a battle to get a permission to have this bigger tower in there. It spoils also, what do they call, there's a term for it, look and feel of that place and all that. So these are difficult challenges, and the advantageous thing for us is the reserve people over there, they are helping us a lot. So I really don't deal with any bureaucratic thing, I don't even sign a single paper. They take care of everything for us over there, and they take care of the cost of the manual labor also, which is a significant part of this effort. Yes.
So when a new team wants to set up a sensor network that can communicate using your backbone, how do they do it? How do those sensors talk to one of these nodes? Do they also have to be on 82.11?
Yes, right now all the sensors, as I said, are audio and video. So we are not talking about the modes or anything. These are like big handful size of sensors, or even bigger than that. Okay. So all have .11 capacity. So they make the 1 hop in there. So getting back to the logistical issues, for every node we need separate permission. It's not a blanket permission that you deploy so many nodes over this area, and they come and inspect every location where we can do it. So obviously, so by definition, and this is what the reserve people have been very helpful, you have to go with the legal definitions of everything. Legal is the key word there. So you cannot have permanent fixtures at many places. Like this place we had to get permission for permanent fixture. This is by definition is a permanent fixture. There are some places like near the pond, it's almost impossible because there are creatures in there, living creatures in there. So if you would have noticed, we'll never get a permission to put a node in here. So the deal is you cannot have a permanent fixture, but you can have what is it called, the movable, there's a term for that. You can have like portable fixtures. So so the idea is, if you look carefully, this and some of the other nodes that you might have seen, this is actually an automobile tire, the entire tire filled with concrete, and then trust me, this is not portable at all. It's so heavy, but by legal definition this is portable, okay, because it's not stuck to the ground, and we have this thing standing, it adds stable, nothing has ever fallen, and we have this pegs around it also. So we have to deal with those kind of issues also in order to bypass it.
Much more severe. You can have spot wind 100 miles an hour.
Oh, okay.
In the summer here, California, much.
Yeah, and obviously that's a pond means that's a low area, so the wind gets shielded by the.
In the Napa Valley, the rain certainly.
Right. Yeah.
No, but they have to do fire.
Yeah. So again, I mean, for example, this one also probably for some reason there's no pond here, but we probably didn't get permission, but you can see our portable node is also there. Okay, so okay, so the solar things, this was also a challenge because I bet like me, some of you will have no clue of how to design a solar system, to power a node, because so they took a lot of learning experience in building the solar power system for this. So finding out what kind of panels you need, how many panels you need, how many batteries you need, what are the ratings and all that. So we got a lot of help from other folks in designing the solar part of it. So these are quite expensive. What you are seeing is actually 4 panels in there. Yes.
So are they like getting dirty and someone has to clean them, and is that the issue, for instance? And then they start losing power?
Ask me in 1 year, I'll answer that. Okay, so it has been probably 9 months or so. We haven't run into that problem, but probably it will happen. But the people at the reserve, they are there, permanently placed, so they could help us in maintaining that. So again, so getting back to this, there are 4 panels in here, and the battery is behind that, and the batteries look like, so this is for the biggest node that you saw. There are 4 batteries. Most of the places we have actually over provisioned. We have put double the number of panels and double the number of batteries that you would need, because we wanted to get with the mindset that, okay, this is what I thought. The persons that were helping me on this, I thought I won't know them probably next year or something. Since I've got some help, let me grab it and over provision it as much as we can, so that once we expand, we will never be having the network down because we don't have enough of solar power in there or something. And it's over provisioned, and if we don't have absolutely no sunlight for 3 continuous days, we'll still have a completely fully operational network in there. 3 consecutive days of no sunlight in California is not going to happen. So
that is our problem in our solar deployment.
Yeah.
We had about 3 hours of power.
Oh, okay.
For the node.
Okay.
That was like the emergency node we did.
No, this has
There was
been
not enough sunlight and we just to do anything.
okay. I mean, for 9 months, we never had we had a lot of problems initially, as with any experimental things of node going down, but not a single time it has because of the power supply. So it's mostly, so that's an interesting issue, that initially with most experimental researchers, although when you present or do things, people focus on how it is working and all that, but a lot of time initially goes on just making it work, okay, because nothing works in the beginning, because there's a lot of problems. Yeah, those of you who have done it, it, and things burn, things go off for no reason, or you cannot find the reason, many times because it's not well packaged or whatever. So and given that it's in a place like this which is not easily accessible, we had to make quite a few runs in order to fix things in there. It's more or less getting more stable as we go along. So I get this usual question, what has been the most difficult part of building the network? It's this, okay, and we get this services free, which otherwise would be the most expensive part of this network, okay. So now any questions about the test beds? So let me flash through a few results in there. Instead of focusing on the numbers in here, I want you to just see what our plans are and what we are providing so far. So we are continually taking all these measurements: throughput, delay, packet losses, signal quality over various links, network utilization we are monitoring, and again, as I said, it can be remotely accessed. And the streaming video cameras, you can, when you go to the website, if you click on the access, we have open access, so you get control of the cameras, you can move it left, right, zoom in, zoom out, and everything you can do from there. And as I said, you can observe from a long distance, you can observe very minute details in there. So we are measuring both throughput and RTT. So again, the names, since you're not familiar, the names you will say it's funny names we have given: field station, DFG hill, and all that. The reason, again, this is out of necessity, is we didn't want to use networking name, because many times we have to call the reserve people that, okay, change that and all that, change that thing and all that, because if we want to save a trip, and they don't understand the networking thing. So if we tell them, go to the Decker Pond node, they know where is Decker Pond, and these ponds apparently have names in there and all that. That's why, but these names tells you, how many, so it maps onto the topology that I had shown earlier, so it tells you how many hops that you are. So in single hops, we sometimes get, we get more than 20 Mbps, which is fairly good. And when you go for a higher number of hops, if you look at this line over here, we get less than 2 or less than 2 Mbps, and this, when we go for 4 hops, we are getting somewhere around 2 Mbps, which is not bad. We can still get streaming video, and you can see, I think we have video cameras at 3 or 4 hops also. The 4th hop video camera is actually an interesting camera in there. There are actually 4 cameras coupled together because somebody is studying 4 insect traps at 4 different locations coupled together, and that has night vision. That's the only thing you can see during night. And as soon as an insect is trapped, it is motion activated, and it takes a picture, sends it back to the researcher. So a lot of interesting applications in there as we are building it, and we are not even halfway through. The other thing that this helps us is actually the reason I have asked my student to keep on looking at this continually is, if there is an error, then if you are looking at it continually, you can figure this out. Look at this, the Decker point somehow is showing low numbers in here correspondingly over here, and if you look at the RTT values also, you can see more than half a second almost in the Decker point corresponding columns and rows, and this is a snapshot of reading at some point of time, and that gave us an idea that, hey, is there something wrong, or this should be real? And we checked, there was something wrong in that node. So it helps us in detecting anomalies in order to detect any kinds of faults in the network, which is eventually, in a long run, this is one of our major goal also, how to detect the malfunctioning, like signal quality deteriorating or something changing as we go along. Yes.
I'm looking at the symmetry between the numbers. I assume that in one case, horizontal is the sender, and then
yes,
so
yeah.
The kind of numbers kind of match. They're not the same.
They are not the same.
Of course, they won't be the same.
That's a good point. I mean, these two numbers ideally should have been same. These two numbers should have been same, but they're not the same because this is again, in most theoretical studies they assume that it's the same, but practically it is not. And that's a good point you pointed out. So you can see that they're not symmetrical.
But you see that in orbitals.
Okay.
So it's because of different interference on the fluid.
Just let me take a pause. You'll see more of that in here because of the more variation compared to orbit. Yeah. What was your question?
I'm saying, is it because of different levels of interference when A is transmitting to B versus B is transmitting to A?
Right, and also the not necessarily signal interference, even the physical interferences. Okay, because it's an outdoor environment.
That should be so.
Those vectors are not symmetrical.
Not just that, you're assuming that you have. This is Hawking.
Any physicist around?
Measure.
Yeah.
Right. So maybe in theory it is, but in fact.
Yes.
Do these values change much over time? For example,
They-
compared to the around network.
They do change, and the changes may not be because of Monday or Tuesday, but because of, let's say, the weather condition changes. And one, do I have the humidity pictures in here? No. One thing that we have seen is there is a strong correlation with humidity, and if you talk to any physicist, they will say, well, obviously, that kind of thing. And as I said, there's a correlation with the wind speed, and that doesn't have any physical reason, but because of the interferences it creates because of the movements. And note that in directional antennas, if they are not aligned properly, that also changes the signal strength. So sometimes if there is a shift in there, that also causes but the other changes we have seen, obviously, if you take correlation between winter time, summer time, there is variation in that. But the reason I'm not pinpointing any exact number is, as I said, you have to mature it over a longer period in order to make concrete statement on that. So these are some of the other snapshots of midday versus night, and actually, this is what will reflect also the change in humidity in here. We also take snapshots of utilization. This is a streaming video utilization snapshot and so on. So again, we are collecting a lot of data, and we are in the process of analyzing some, and we'll analyze more. And so those are for the data analysis point of view. For the research, we are doing other things. So I'll change gear to the next issue in here on the research side of things. So again, I have this is you'll think that, oh, this is a long list. I have about 12 PhD students, so ends up translates to a lot of projects. So here I am focusing only on the work that we are doing on the wireless networks. I have couple other projects on the wired side. One is on internet measurements. If you are interested, we have a paper in SIGCOMM coming up in 2 weeks from now. The other area that we are looking at is on DNS security. So you might be familiar with phishing and pharming attacks. So we have proposed a cute solution for countering the phishing and pharming attacks in DNS. You know what phishing attacks are, right? When the DNS is faked by somebody. Okay, so moving back to the wireless things, we are. So obviously I won't talk about all of these. Okay, I'll talk about a few of these, but I'll give you, an overview explanation of some of this. This is a DoD project that got funded this year, a 5-year big project for enhancing resiliency and security in mesh network. So DoD's problem is as such, they're not worried too much about performance. Okay, they use their own spectrum and probably have better gears for that. What they are concerned about is in multi-hop communication, the robustness, that it should work like a wired network. We have not reached close to that. Can we make it fully robust that, you rely it as much as you rely it, not probably as much as like wired LAN telephone line, but like, wired connections. Okay. So, and security is another thing. So we have a big group of people working on these issues. My group is mainly focused on the robustness issue. We did some theoretical work on capacity enhancement, multi-radio, multi-channel configuration. So contrary to most of the other work, I'm currently moving more towards scheduled MAC rather than CSMA type of MAC. Okay, so there has been a lot of work done on CSMA type of multi-radio, multi-channel configuration work. So we are looking more in terms of scheduled MAC. We have 2 projects funded by Intel, WIMO, and SWIM. I think I have slides for this. I'll talk about that. SWIM is basically, the idea is when you have a large corporate environment, if you create a mesh using the wireless routers, so what happens is initial deployment you will do probably uniformly distributed or whatever way you want. But because of the mobility of people, if you have a conference, if I go to give a talk at Intel in a conference room, everybody comes with their laptop because they are surfing the net while I'm talking. So the nearby access point will get overloaded. Okay. Same thing will be with the gateway. Similarly, during the lunch hour, the access points near the cafeteria get overloaded and so on. So our goal was to have a dynamic load balancing schemes in a mesh network so that you won't have those overloading situations. So that's the problem that we are solving under SWIM. We are doing a bit of work on WiMAX network. So I forgot to mention regarding the Quail Ridge, we are in the process of expanding now in 2 different ways, increasing the number of nodes, and also there is another reserve which is about 45 miles away from Quail Ridge that is also owned by UC Davis, a smaller one. We'll put a small mesh network over there, somewhere around 8 to 10 nodes, and we'll have these 2 connected through 3 hops WiMAX nodes. So we need actually 2 WiMAX nodes, and we are not being able to get it as I speak. So we have found 2 locations where we have got permission to put WiMAX nodes. So we'll have a 15-mile long WiMAX hop and another shorter hop and all that. So that's in the plan as and when WiMAX becomes available / affordable. So we are looking at scheduling in WiMAX node. Note that WiMAX is already scheduled MAC, not like .11. I'll talk more about video over mesh kind of support. We are doing in the bottom 2, I have results in there too also. So I'll talk about the bottom parts over there. So okay, so this is something work that we recently published actually on maximizing. This is more on the theoretical side that here is the problem. Let me, for most of the following things, I'll pose the problem and leave the solution for offline. So if you have multiple nodes, if you have a mesh, each node has the capability of M radios and you have N channels at your disposal. How will you allocate the interfaces? Interfaces means that many radio. How will you allocate the interfaces and the channels to maximize the capacity? Okay, there are obviously constraints. If you have, let's say, 2 interfaces of this node, then you can use only 2 channels maximum. And if you want this node to have a link with this node, at least one of the channels in each of them should be the same. Okay. So, there are some there are these constraints. Based on those constraints, how you can maximize the capacity in a scheduled MAC environment. Okay. So, that is the the again it is an NP complete problem. So, we are using heuristics in order to find out better schemes in order to maximize the so the
So, what is
yeah.
flight capacity? Is the sum of the rates all of it?
No, no. So, what we are doing is different than others is we are doing flow based. So, if you have multiple flows, then what is the maximum flow rate that you can provide to a flow?
Okay.
That is the type.
Capacity is the sum of the flows.
The capacity is the sum of the flows, yeah, but this is how we defined it, but in traditional sense, when you are looking at the absolute capacity and all that, it's actually the entire network capacity link by link basis. Okay. So, the WIMO project that as I said, this is an Intel sponsored project. So, the idea is in many cases, like our QuRiNet and unlike Orbit, you probably do not have the luxury of having a wired control plane. Okay. And again, in real network you will not have that luxury. In test beds you will have it, but in real network if you have wired network, then why have wireless? Okay. So, if you do not have that, then the management becomes a challenge, because management is a challenge in wired network also, in wireless more so because it consumes extra bandwidth. Not only that, it interferes with the transmissions nearby. So, the goal here is what we tried to do is we had a kind of an overlay. So, we have this monitoring agents, what we call them. These monitoring agents are in a subset of the mesh, and there is a kind of an application layer network established between the subset of this node to take care of the management functionality. So, what we are trying to do, what we are trying to answer in this problem is how many such agents that we need, or I mean for example, we are doing a scale. If the best case is have these agents in all the nodes, but if you go down, how much of management functionality can you give up and still tolerate? So, we are trying to find out a trade off in that sense, that if you can have less number of nodes having this management agent and still satisfying the managing conditions, then you can also reduce the interference with other communication and so on. So, that is the goal of this ongoing project. This is what we are doing in the context of multi-hop WiMAX networks, and so far all our work on WiMAX based things are simulation, because we do not have any testbed support on for WiMAX. So, we are using heuristics algorithms for tree based multi-hop WiMAX networks. So, we are doing scheduling both on uplink and downlink. So, we have a paper in MAS 207 this year coming up on this. Okay, so talking about QoS support in wireless mesh. So, many evolving applications, they need quality of service support, and again first thing that comes to mind is, well, .11e was developed to enhance quality of service in wireless network. That is true, and but before I get to shooting down that idea, is here is the difference. Again, I think most of you know this. .11 is this: you have a single queue, the distributed coordination function Q, and then it uses these three parameters: backup interval, interframe space, and the contention window. These three parameters in order to schedule or send the traffic to the network. Now, in .11e, again just I am giving a 30-second tutorial. What the standard says is you break it up into 4 queues now. Each queue will use its own set of parameters, and by tweaking these parameters you have shorter backup interval here, shorter interframe space over here, shorter contention window over here. So, it is more likely that a packet from here will get scheduled to the network faster than this queue, correspondingly from this queue, and this is. So, this is kind of a very high level view of how .11e works, and they classify based on the type of traffic, whether it is best effort or video or whatever, they classify into one of these queues. Okay. So, that is how the service differentiation is given. However, .11e is designed for single hop environment, and it does provide single hop service differentiation, but it has no notion of end to end quality assurance. Okay. So, our goal was to extend it for multi hop networking environment. So, this is how we did it. Again, without going to the slides, like 15 years back I was more working obviously on the wired part. So, In the Internet QoS domain, there were two competing architectures, IntServ and DipServ, integrated service and differentiated service. I was in the DipServ camp, so I'm borrowing idea from that knowledge. Is what if we, so let me give you a trivial example over here. Let's say we are considering end-to-end delay as our QoS requirement. Let's say my end-to-end delay requirement is 50 and I'm running a source routing protocol. So I know I have to make 5 hops. So my per hop budget, I don't have to split it equally, but I can say my per hop budget is 10. So every hop, my first hop I have to make in 10 time units, second hop within 20 time units and so on. If I do that, then I'll meet my end-to-end QoS requirement. So at every node, I look at the laxity from your budget than what you have actually consumed. So it will need one extra field in the header. How much you have consumed, how much time, what was your budget, difference of that will give you the laxity. The one that has most negative laxity will get the first priority queue and so on. So your priority could keep on changing at each and every hop. Okay, this is, as I said, is borrowed from the DipServ architecture. So by doing that, you can have this end-to-end requirements embedded into the scheme. And the other nice thing is you are not changing the standard, you are running it still over .11e standard. The only thing that you do is the way you allocate a queue, you keep on changing that at every hop. Okay, so
it's like the EDF, 5 years deadline first.
Right, yeah. So we smartly adjust the packet priority level at each hop so that the priority is not too high, not too low, and it meets the end-to-end delay requirement. So again, we went through a detailed implementation type. Let me show you the simulation results, and we are actually deploying it in our testbed to test it out. So just to show the difference between if you use .11e and our scheme, which we call adaptive per hop service differentiation, APHD, some things may not be that readable from back there, but the top pictures are all from the EDCA. So .11e, this is our scheme. So if you look at the end-to-end delay at low loads, both of them work the same. So we can claim that our scheme works fine. But if you look at higher loads, I forgot what was the delay requirement over here, but some of the flows miss the deadlines, whereas in our scheme the deadlines are still met. Same thing correspondingly, you can see the throughput also. At low load everything works fine, but at higher load the throughput requirements are met more satisfactorily in our scheme compared to if you are using .11e for multi-hop environment. So again, we're using different priorities and all that. So again, I'll just flip through these results. Same kind of observation that you have. Now we have some, so those are over CSMA because using .11e we are doing. We did some work on yes.
So equal to 11e.
Yeah.
It works for infrastructure mode. So
yes.
What happens when you have an ad hoc routers competing for the channel does this kind of result?
So again, .11e, as you said, was designed for single hop infrastructure based LAN, and it works fine in there. When you have this multi-hop communication, it wasn't designed for that. So what happens is you could have at present since you have assigned the priority at a node, somebody who is way ahead of its goal, of its QoS requirement, might still get higher priority over the ones which, if you bump it, could meet the requirement.
Yeah, but I think the problem comes in some of you have a distributed control among the ad hoc nodes.
Mm-hmm. No, I have the results for the grid topology also, and I cut down some of the graphs, but yeah, we have looked at the grid topology, other kinds of topology. It does help in that also. So the routers don't have to cooperate here because that information is in the packet header. So in the packet header, one key thing I said, this only works for source routing protocol. You are carrying the expiry time and the time that you have consumed.
Yeah, so it does, the problem is it's only not problem. Works for source routing.
Right, yeah, that's what I said, yeah. Yeah, it will work for source routing protocol, yeah.
Is that expected time on delivery?
Just the lags.
Just lag, but
carry the lag.
use absolutely
Yeah.
Pick the one with the most negative.
But who is going to pick?
local route.
Local route.
Where 3 routers communicate.
No, no,
No, no, no, no,
It's
no.
only local. It's call by call.
Yes, hop by hop, but each router might give the one with the lowest expiry time.
Right.
But the second router doesn't know
Yeah,
which one in my queue is first, right? So that guy will put whatever. So those
Yeah,
two
will
packets
shuffle.
will,
Every
those
router
two
will
packets
shuffle.
will still have random access contention. The packet from router A and router B.
What is
No, but
after
they
the
don't
packet
have-
arrives?
It's a linear structure, so
In a linear structure, yes, but if the 3 routers with
I see what you're saying.
No.
each
Even,
router will have some EPP ordering and
right, and then they will dump the packet into given node, right?
each node will just decide which.
No, no, Sanjay, he's talking about a different problem. You know, each
You
package
want
does
the
this,
hierarchy,
yeah,
and then you
yeah,
have-
it's that's in the different level of hierarchy. If you know you are doing your own scheduling, I am doing my own scheduling, then we do channel contents and access. Then you might get priority, whereas I could be better by. But yeah, that's another level of scheduling.
Maintenance with priority.
Right,
But
right,
that's a
yeah,
multi-hierarchy thing.
yeah,
As
yeah.
soon as you do that, you have a problem with coordination.
Yeah.
That's
And in fact, Ray, in the grid environment, we have seen that, you know, although we are better than .11e, but you know, we miss some of those. Yeah, we miss some of
You
those.
have more hierarchical,
Yeah.
the more of these things get.
Yeah. You have a question? No? Okay, so we looked at, so another issue we looked at is a good admission control scheme coupled with QoS aware routing. So the idea is, okay, before that, you know, you already know this, you know, if you have multiple flows, you have interflow interference as well as intraflow interference. The flow interferes with itself, the current hop interferes with previous hop. So these are some of the results that quantifies this interference, that, you know, this is really a problem. Okay, given this audience, I won't spend any time convincing it. So this is one approach that we used in order to do it. And again, you know, this approach has some problems also. I'll tell you what it is after I go through the approach. So you take a graph, take the network graph, wireless network graph, convert it into the conflict graph. You know what conflict graph is? A link in the network graph is a node in the conflict graph, and an edge detects A and B are conflicting with each other. B and F don't conflict, so there is no link between them in the conflict graph. So from the conflict graph, what we create is called cliques. So there are two constraints that we put in. One is, so what we are trying to do is admission control over MS. So given if we identify a path for a flow, for an entire flow, we find out the residual bandwidth in that path. And here, it's unlike the wired environment, it's not only the bandwidth of that you check in the path, but also you should check if you are interfering with other flows, you are not impacting them to an extent that those will get affected. So in maximum click constraint that we use, the idea is, again, as I said, we are changing to time domain access now, not CSMA. So in every time slot, not more than one link of a click can be active. Okay, that's the restriction. So using both the restriction, we do some admission control over there. And again, you know, there are other details to be worked out for this to be worked, and I'm skipping those on how do you find the, how do you integrate this with the routing scheme and so on. We have this in a Mobiquitous paper. So one thing I want to show over here, we have some simulation results, and also I will show you some real results using video traces. So again, we have done grid networks. So these are all simulation results, where basically what we are showing is, if you don't do admission control, by just admitting this request, you messed up the throughput of all the flows, whereas just by removing only one request, you could have met the requirement of all the flows. Okay. Same thing we have seen, you know, just by dropping here, probably all of them miss their deadlines, but just by dropping one flow, you could have all of them meet the deadlines and so on. So again, let me show you the real trace results. So we are plotting it with frame. These are with corresponding to each of the frame. What is the PSNR? Okay, peak signal to noise ratio, and we have 2 background flows and 3 video streams. So what we have seen, okay, in our scheme with admission control, if we drop one flow, so then the blue one is the variation over there. If these results don't make any meaningful sense, this is the difference that you see with, by dropping one flow, we have this, by admitting all the flow, we have the left side. In the second experiment, we said, okay, we have both the things. So just to show the impact of finding a QoS aware route. So, we admitted 2 flows in both cases, one with QoS with the same background noise, one with QoS aware path, another is whatever path is available, and these are the differences of PSNR, and this is the quality difference that you can see as matter of perception. Okay. So, the other work, we did a detailed work, and we think we submitted this work to Infocom this year. So, we are analyzing link behavior for various traffic conditions, modulation rates, and many other variations. So, we just took a simple experiment. We just took 2 links. Okay. Basically 2, you can make only 2 hops. So, we wanted to do a very micro level analysis on what happens in the 2 links without any interference, when you have intraflow interference, when you have interflow interference. With the matrix that we are looking at is what are the channel conditions, how many retries that you have, how many frames you are getting queued, and what is the relationship with when you are having packet drops and so on. Then we also defined a term for modified transmission time, which is basically you transmit, and it includes the queuing time, retransmission time, until it is eventually received correctly. So, again, these are some of the experimental situation. We use different modulation rate 1, 36, 54 Mbps, different types of frame sizes, and again there are a lot of results that we have produced in here. I will show you a few results. So, one thing you notice that if you have a non-interfering scenario, very few, less than 1% of the frames fail on the first try. Okay. And we are again, in this case, I probably don't have the results in the slide. We are measuring the RSSI both for the forward direction and the reverse, because your reverse is as important as the forward, because unless you get an ACK correctly, it's no use if your data reach the other side correctly. Okay. And there were interesting results showing that, and you can see that in this case, probably not so much in here, but again, this is showing the RSSI of the ACK and the data, and correspondingly how many retries that you will have over here. These are at least 2 retries, these are the purple ones have at least 3 retries, and so on. So, we
are this with scheduled map or with CSMA?
No, this is CSMA. Yeah, this is CSMA. So, the other things,
there should be some like self interference in terms of like data and ACK interfering with each other.
Right, yeah.
We have seen that in
and actually the first one that I showed over here is actually for one, there is only a single hop, and then you will obviously have ACK of the previous one versus the current data and all that. So, those are very interesting results that we have also found. So, if you go for the intraflow interference, we could see that due to interference, the frame needed to be, again the legends are not readable. So, what this is saying is for first hop and second hop, this many number of frames needed to be retried once more, this many twice, this many 3, 4. There are some hops that needed 7 tries, after which we are aborting it. So, again, so we had for different kind of modulation, this is 2 hops 54 modulation rate in one, and the next one is the same. Then there are 54, 36. So, these 2 numbers are 2 different links, 54, 6, and so on. We have other combinations also in our paper. Similarly, we are also looking at 1 hop interflow interference if you create another flow to interfere with it. So, you can see that both the flows will need retries. So, both the flows are affected, more than 20% of their frames are retried, and we have corresponding details overlaying this along with the RSSI of the data as well as the ACKs. So, here you can see the okay, this is a 2 hop interflow interference issues. So, one thing I want to point out over here, each node has about, because of the fairness in dot 11, each node has 1/3 of the channel, okay, which is actually a drawback of dot 11 for multi-hop communication, because if you look at this, the throughput is pretty much, it's getting balanced out, the queued frame is getting balanced out. If you look at the dropped frames per second, it's way higher in the B node, which is the middle node, okay. Part of the reason is because this is relaying packets from both sides, should have more channel, access time, but that is not allowed in .11. That's why it's dropping more frames compared to the other nodes. There's another interesting study that we are doing. One of our goal, I didn't mention this earlier, eventually the context of QueRiNet is to develop good tools for both for development, for measurements and analysis actually. So we want to we haven't done much, but what we have done so far is since quite a bit of our work is focused on QoS type of service provisioning, one measurement we always need is what is the available bandwidth of a link. Okay, there are different ways of computing it. There are a lot of times, and in fact when you do any QoS kind of admission control or anything like that, I'm running over time, but I'll finish quickly. You will, most of the time, you are not worried about what's the total capacity, because that's where most of the focus is. You are worried about, I need this much bandwidth, is it available? So the available bandwidth of a link relates to the spare capacity, and again we know what capacity is. So this is a topic of great interest. Now all the QoS our applications will need this. So we wanted to see what can be done in this area. So that we looked at, there are quite a few tools in available bandwidth estimation for the wired network, and these are some of the, if we look at all the tools, we could classify them in two broad categories. One we call as probe gap model, other is probe rate model. Probe gap model is, I'm giving you a very abstract idea of that, is you send two probes back to back and at the end you see what difference they arrive. Okay, that's how much gap is there. The probe rate model is you keep on pumping the network and see how much rate it can sustain. Okay, it's a very high level view of what these two models means, and there are these different tools that have been proposed and have been successfully analyzed in the wired environment. Path load is based basically on the I think path load and path chirps are based on the what was the second one? The probe rate, and the other two are based on the probe gap. Okay, so again there are variations between these four schemes. Again, in the interest of time, I'm not going to the details. So our goal was, let's take these things, these measurement tools that have been analyzed already, let's see how they behave on mesh networks. So we created a small configuration, and eventually we'll do the same set of experiments in the Quail rich network to see the differences. So we wanted to we used .11a to avoid interferences from the nearby network, and we evaluated each tools at different modulation rate with and without capacity, with and without cross traffic. So we use iperf. I'm not saying that iperf is the best tool, but we use iperf and ThruLay, these as kind of the base comparison, as has been done in some of the other studies also. So these are for the different modulation rate, and this is the measured available bandwidth that we see. Okay, so as you go on increasing the modulation rate, the available bandwidth increases obviously. So again, the legends are not very clear. The last two are iperf and ThruLay. So these are our base comparison for that, and the other fours that we have, these four are the tools that we wanted to compare. So we could see that at low modulation rate, most of them they perform reasonably well, but as we go on increasing the modulation rate, the IGI PTR and Spruce is performing well. The path load and IGI PTR, these two form the difference from the ideal one is, or from the better one, is quite high. So as we go higher and higher, we see path chirp is the one, that is the only one, and Spruce to some extent it's coming, but eventually path chirp is the only one that is showing better available bandwidth as compared to the other two, compared to the standard matrices. If we take the cross traffic also, we could see that Spruce is performing as good as path chirp. Okay, but the path load really deteriorates when there cross traffic. Path load becomes like a useless measurement tool in that case. So we have looked at again two hops. Now these notations are as follows. This is the highest we saw, lowest, the mean one, and this is the 25th to 75th percentile. So we have two wireless hop between source and destination. Each link is using orthogonal channel. So here we have compared it with iperf is over here. So you can see that Um, Path chirp is again probably closer to iPerf compared to other one, although spruce firm better. This is without cross traffic. Okay. Again, you can see that the path load is not good in this environment also. Now, when you include the cross traffic, then you can see that. Oh, I'm sorry. Yeah, in 3 hops, as you go on increasing the number of hops, which spruce was performing better for low number of hops. With increasing number of hops, now spruce dropped down. So again, the next step is to analyze why it is happening. That will help us. So again, this is what I was telling earlier. The goal here is by doing these kind of analysis, we will get guidelines on what to develop next. Okay. So we have this with cross traffic. So you can see again, in most cases we have seen path chirp comes closer. In this one, I didn't plot spruce because there was some abnormality in there, and this is as we speak. My student is working on this. I couldn't get that result. So again, this gives you the intention here is to give you a picture of what all we are working on. So let me end the talk with concluding remarks. There are applications for mesh networks still evolving. Some issues that will be more important is interoperability. We have Wi-Fi everywhere. WiMAX will be dominating also. Bluetooth is there. There was Nokia shipped 1 billion cell phone last year. So most of them with Bluetooth capability. Cellular network is there. All this is creating a wireless mesh. This time it's MESS. So how do we interoperate between them? Interoperability in 2 different dimensions. If I have a cell phone which has 4 radios. Infrared, Wi-Fi, the cellular radio, and the Bluetooth. So can I opportunistically use one versus the other as I'm moving from different environment? The other type of interoperability is there could be one flow, could be starting from your cell phone into let's say using Bluetooth from your PDA, then Wi-Fi, then WiMAX, then wired, and all that. So how do you interoperate between those type of networks? All this multi-star stuff, multiple channel, multiple radio, multi-path, multi-flow, multi-layer, multi-rate transmissions, multiple antenna, MIMO, all this you need to have protocols, MAC protocols and routing protocols. Although I would say enough of routing, let's focus more on things lower than routing. We need to, if we cannot enhance the capacity because of physical limitations, we need to exploit. Can we exploit some of these issues in order to enhance the capacity? Recently, Ed Knightley and I, we headed a group of community feedback to NSF on experimental and measurement based study. There was a lot of emphasis put by the community on real good experimental studies and experimental setup. The other thing that I'm also focusing now is on robust and secure communication, because if there is not enough, if I walk into a hotel, even now, if there is if there is Ethernet cable lying, and although they have wireless connectivity, if I'm in the room, I tend to plug in the Ethernet cable because I know it's not going to fail, it's work, high bandwidth and all that. Can we have that kind of reliance on wireless? Once we have that, the adaptability will also increase. More than anything, what I want to emphasize over here is, although more than 3/4 of the research is focused on improving the capacity, throughput, delay, and all that, robustness is one issue that needs to be emphasized more. And again, this is what I tell my students, let's look at all the needs of the users rather than focusing on the performance. We always focus on improving the performance because, trust me, that's most easy to do compared to other things. For robustness, first we are now debating, how do I say my network is more robust than Sanjay's network? Performance, you can easily say I get better throughput than his throughput, but robustness, what does it mean? So one thing that we need to worry about is what the user needs. The user needs all these things. The user needs security, portability, interoperability, scalability, reliability, ease of use. This is a big thing. Okay, if Orbit is not easy to use by other researchers, they will not use it, irrespective of how good it is. Of course, we all deal with speed issues, and you always have to worry about all these issues with the bottom line constraint of the cost. Okay, thank you.